What if I told you a 17-year-old kid from New Jersey revolutionized drag racing with nothing more than a piece of scrap aluminum and a drill press? While professional race teams were spending thousands on complex nitrous systems, this teenager built something in his garage for $60 that would make their expensive setups look like overkill. This is the story of how Mike Thermos outsmarted the entire racing industry. Picture this. It's 1981, and the parking lot behind a strip mall in Edison, New Jersey, is packed with muscle cars. Engine revs echo off the buildings as street racers line up for another midnight run. Among them is a skinny teenager leaning against a primer gray 1970 Camaro. While other racers are bragging about their cam profiles and compression ratios, Mike Thermos is quietly bolting something between his carburetor and intake manifold. It's just a flat piece of aluminum with some holes drilled in it. The other racers laugh. Then he fires up the engine, hits a button, and suddenly that Camaro sounds like it's breathing fire. The laughing stops. This is the story of the nitrous plate system, a beautifully simple innovation that democratized horsepower and proved that sometimes the best engineering solutions come from teenagers working with scrap metal, not million-dollar R&D departments. To understand why Mike Thermos's invention was so revolutionary, we need to understand what drag racers were dealing with in 1981. Nitrous oxide had been around since World War II, when German aircraft used it for high-altitude performance boosts. By the 1970s, American drag racers had adopted it as the ultimate power adder. The science was simple. Nitrous oxide breaks down at high temperatures, releasing oxygen that allows you to burn more fuel. More fuel plus more oxygen equals more power. Simple in theory, expensive and complicated in practice. The dominant nitrous technology in 1981 was direct port injection. This system required drilling and tapping the intake manifold with individual nitrous and fuel nozzles for each cylinder. We're talking about precision machining on your intake manifold. One mistake, and you've ruined a $300 part. The nozzles themselves cost $40 each, and you needed 8 of them for a V8. Add in the distribution blocks, the braided lines running to each nozzle, the solenoids, the jets, and suddenly you're looking at a $2,000 system. That's about $7,000 in today's money. Installation was a nightmare. You had to remove the intake manifold, drill 8 precisely located holes, tap threads into cast aluminum or iron without cracking it, install the nozzles at exactly the right angle, plumb individual lines to each nozzle, and then tune the fuel and nitrous delivery for each cylinder. Professional shops charged $500 just for installation, and that's if nothing went wrong. The average street racer couldn't afford it, and even if they could, most didn't have the tools or expertise to install it properly. But here's where it gets interesting. Even with all that complexity and expense, direct port systems had problems. Distribution was never perfect. Cylinder number 3 might run rich, while cylinder number 7 ran lean. The multiple connection points meant multiple potential leak points. The spider web of lines under the hood made other maintenance a nightmare. And if one nozzle clogged during a run, best case, you lost power. Worst case, you melted a piston. Enter Mike Thermos. He wasn't a professional racer. He wasn't an engineer. He was a 17-year-old kid who spent his weekends street racing and his weekdays working part-time at a machine shop in Edison. Mike couldn't afford a direct port system, but he understood the basic principle: get nitrous and fuel into the engine. While watching his carburetor work one day, he had an epiphany. The carburetor was already doing the hard work of distributing fuel evenly to all cylinders. What if he could piggyback on that existing system? His solution was brilliantly simple. Take a flat piece of aluminum about ½ an inch thick, machine it to match the carburetor base gasket pattern, drill 4 holes through it, 2 for nitrous, 2 for fuel. The holes would spray the nitrous and fuel directly under the carburetor butterflies, where the high-velocity airflow would atomize and distribute the mixture naturally. No individual cylinder nozzles, no complex plumbing, no precision manifold drilling, just a plate. Mike's first prototype was literally made from scrap. He found a piece of half-inch aluminum plate in the shop's scrap bin. Using the shop's mill during his lunch break, he machined it to match his Holley 650 carburetor. The pattern was simple: 4 mounting holes for the carburetor studs, a center opening matching the carburetor bores, and 4 small holes drilled at specific angles to inject the nitrous and fuel into the airstream. Total machining time, 45 minutes. Total material cost, 0, since it was scrap. Add in the fittings to connect the nitrous and fuel lines, $60. The theory was elegant. As air rushed through the carburetor at wide-open throttle, it created a low-pressure zone beneath the throttle plates. Mike's injection points were positioned to spray directly into this low-pressure, high-velocity zone. The nitrous would instantly vaporize, cooling the intake charge by 200 degrees. This cooling effect increased air density, allowing even more oxygen into the engine. The supplemental fuel would mix with the nitrous fog, creating a homogeneous mixture that the engine's normal intake flow would distribute evenly to all cylinders. But theory is one thing. Testing is another. Mike bolted the plate to his Camaro's 350 cubic inch small block. The engine was nothing special. A rebuilt unit with flat-top pistons, a mild cam, and about 9.5.1 compression. On motor alone, it made maybe 325 horsepower. He connected a 10-pound nitrous bottle in the trunk, ran a single feed line to the plate, added a fuel line from a pressure regulator, and wired up a micro switch to activate the system at wide-open throttle. The first test run was in the machine shop parking lot after hours. Mike started with conservative 50 horsepower jets. He mashed the throttle, the micro switch triggered, and the engine responded like someone had hit it with a cattle prod. The rear tires broke loose instantly, sending the Camaro sideways. After shutting down and checking everything, Mike discovered the plugs showed perfect combustion, no signs of lean or rich conditions on any cylinder. The distribution was working. Over the next few weeks, Mike progressively increased the jet sizes: 75 horsepower jets, 100, 150. Each step up required recalibrating the fuel pressure and ignition timing, but the plate kept delivering smooth, consistent power. By the time he reached 200 horsepower jets, his mild 350 was putting down over 500 horsepower at the rear wheels. The local street racers couldn't believe it. This kid with his homemade plate was running door to door with big blocks running expensive direct port systems. Word spread quickly through New Jersey street racing underground. Racers started showing up at the machine shop, asking Mike to make plates for their cars. He charged $150 per plate, enough to cover materials, machine time, and a decent profit. Compared to a $2,000 direct port system, it was a bargain. Installation took 30 minutes instead of 8 hours. You didn't need to modify your intake manifold, and it worked. But the real test came when professional racers started paying attention. At a grudge race in Atco, New Jersey, Mike's Camaro lined up against a purpose-built Mustang running a full direct port fogger system. The Mustang's owner had spent $15,000 on his engine, including the $3,000 nitrous setup. Mike had maybe $3,000 total in his entire drivetrain, including the $60 plate. The flag dropped. Both cars launched hard, but by the 60-foot mark, Mike was pulling ahead. He won by 2 car lengths. The Mustang's owner was furious, then curious, then amazed. He couldn't understand how a simple plate could match his expensive system. Mike explained the physics. In a direct port system, each nozzle creates a localized cooling effect in one runner. The plate system cools the entire intake charge uniformly. Direct port systems can suffer from distribution problems if one nozzle flows slightly different than another. The plate system lets the carburetor and intake manifold do what they're designed to do: distribute mixture evenly. Direct port is like 8 people trying to coordinate pouring water into a bucket. The plate system is like using a funnel. The science backed up Mike's real-world results. Testing showed that the plate system's nitrous fog increased the intake charge density by 30%. The fuel atomization was actually better than direct port because the fuel had more time and turbulence to mix with the air and nitrous. The temperature drop across the plate created a natural intercooling effect, and because all the nitrous entered at one point, tuning was simpler. 1 set of jets instead of 8. By mid-1982, Mike had sold over 200 plates. He'd expanded beyond the basic Holly pattern to make plates for Rochester, Carter, and Edelbrock carburetors. Each design required careful consideration of the carburetor's airflow patterns. A quadrajet needed different spray angles than a Holly. A spread bore required different positioning than a square bore. But the fundamental principle remained the same: inject into the high-velocity, low-pressure zone and let physics handle the distribution. The established nitrous companies initially dismissed the plate system. They'd spent years developing and marketing direct port systems as the ultimate in nitrous technology. How could a simple plate compete? But as more racers switched to plate systems and kept winning, the industry had to pay attention. By 1983, NOS, the biggest name in nitrous, introduced their own plate system. They called it the Power Shot and marketed it as a breakthrough in nitrous technology. Mike didn't have a patent. He couldn't stop them. Within a year, every major nitrous company offered a plate system. The technical evolution of the plate system is fascinating. Mike's original design used straight-shot nozzles. The nitrous and fuel sprayed perpendicular to the airflow. Later designs introduced angled nozzles that sprayed at 45 degrees, creating better mixture motion. Some plates added secondary fuel circuits for progressive enrichment. Others incorporated burst panels for backfire protection. But the core concept, Mike's concept, remained unchanged. Testing at Holly's R&D facility revealed just how efficient the plate system was. Using high-speed cameras and pressure sensors, engineers documented the nitrous fog formation. The footage showed a perfect cone of atomized nitrous and fuel expanding beneath the carburetor with uniform distribution to all barrels. Pressure readings confirmed equal nitrous delivery to all cylinders within 2%. Temperature probes showed consistent cooling across all intake runners. The simple plate was achieving what direct port systems struggled to accomplish with far more complexity. The plate system had another advantage Mike hadn't initially considered: safety. Direct port systems inject nitrous directly into the intake runners, very close to the combustion chambers. If backfire occurs, the flame front has a direct path to the nozzles and potentially back to the solenoids. Plate systems inject into the plenum area, with the carburetor butterflies acting as a natural flame arrestor. The larger plenum volume also provides more space for pressure dissipation during a backfire. It wasn't uncommon for direct port systems to blow intake manifolds apart. Plate system backfires usually just pop the carburetor butterflies open. Professional racers started recognizing another benefit. Plate systems were easier on parts. The uniform mixture distribution meant more consistent cylinder pressures and temperatures. Direct port systems often showed significant variation in piston and valve temperatures between cylinders. Engine builders found that engines lasted longer with plate systems, especially in street-driven applications where consistent tuning was difficult to maintain. The cost difference was staggering. A complete direct port system in 1982 cost between $2,000 and $3,000. Installation added another $500. Replacement jets cost $20 per set, and you needed 8 sets for tuning. A plate system cost $200 complete. Installation was free if you could turn a wrench. Jets cost $5 per set, and you only needed 1 set. For the price of one direct port system, you could set up 10 cars with plates. Mike's invention democratized nitrous oxide. Suddenly, any kid with a decent small block and $200 could add reliable horsepower. The street racing scene exploded. Cars that previously ran 14-second quarter miles were suddenly running 12s. 12-second cars were dipping into the 10s. The performance threshold for being competitive dropped from needing a built big block to having a decent small block with spray. But the real revolution was in bracket racing. Bracket racing is about consistency, not outright speed. You predict your elapsed time, and whoever runs closest to their prediction without going faster wins. Nitrous systems were traditionally terrible for bracket racing because the bottle pressure dropped as it emptied, causing inconsistent power delivery. But plate systems, with their simpler flow paths and a single point of injection, were more predictable. Racers could compensate for bottle pressure changes more easily with a plate than with 8 individual nozzles. The tuning simplicity was revolutionary. With direct port, if cylinder number 5 ran lean, you had to pull the intake manifold, change that specific jet, and reinstall everything. With a plate, you changed 2 jets accessible from the top of the engine. If you wanted more fuel, you increased fuel pressure or jet size. If you wanted less nitrous, you decreased nitrous jet size. The entire system could be tuned with a jet kit, a fuel pressure gauge, and a spark plug reading. Mike's plate also solved the progressive nitrous problem. Racers wanted to start with less nitrous to avoid overwhelming the tires, then ramp up to full power. Direct port progressive controllers were complex and expensive, requiring individual solenoid control. With a plate, you could use a simple time-based progressive controller that gradually opened, a single nitrous solenoid. The cost difference was $1,000 versus $150. By 1984, the plate system had become the de facto standard for carbureted nitrous applications. Mike Thermos, now 20 years old, had revolutionized an entire industry. But rather than capitalize on his invention, he made a choice that defined his character. He continued working at the machine shop, making plates for local racers, and never pursued the fortune he could have made. When asked why he didn't patent the design, Mike's response was simple: "I wanted everyone to go fast, not just rich kids." The technical specifications of Mike's original plate design reveal its elegance. The aluminum was 6061T6, chosen for its machinability and strength. The plate thickness of .500 inches provided enough material for the spray bars while maintaining structural integrity. The nitrous holes were 0.125 inches in diameter, drilled at a 15-degree angle to create optimal spray pattern. The fuel holes were 0.093 inches, sized to provide the correct fuel-to-nitrous ratio with typical fuel pressures. The total airflow restriction was less than 1%, negligible compared to the power gain. The spray bar design was critical. Mike discovered that extending the nozzles slightly into the airstream improved atomization without significantly restricting flow. The bars protruded 0.250 inches into the plenum, positioned to spray just below the carburetor's booster venturis. This positioning took advantage of the existing fuel signal from the carburetor, enhancing mixture motion and preventing fuel puddling. Temperature management was another key innovation. Mike's plate design incorporated heat isolation grooves that limited heat transfer from the intake manifold to the plate. This kept the nitrous cool until the moment of injection, maximizing the density increase. Some later designs added phenolic spacers for even better heat isolation, but Mike's original grooves provided adequate thermal barrier for street applications. The physics of nitrous oxide injection are fascinating. N2O exists as a liquid under pressure in the bottle at around 760 psi at 70 degrees Fahrenheit. When it passes through the jets and experiences the pressure drop, it instantly vaporizes, absorbing massive amounts of heat. This phase change drops the temperature by up to 300 degrees Fahrenheit. The cold, dense charge can increase oxygen content by 50% compared to naturally aspirated operation. But nitrous isn't just about oxygen. The nitrogen component acts as a combustion moderator, preventing detonation that would occur with pure oxygen injection. At combustion temperatures, the N2O molecule breaks apart, releasing the oxygen for combustion, while the nitrogen absorbs heat and slows the flame front. This controlled burn rate is why engines can survive massive nitrous shots that would destroy them with equivalent supercharging. Mike's understanding of these principles, despite lacking formal engineering education, was remarkable. He intuitively grasped that successful nitrous injection required three things: proper fuel enrichment, adequate fuel atomization, and uniform distribution. The plate system achieved all three with mechanical simplicity that bordered on elegance. The cultural impact of the nitrous plate extended beyond just performance. It changed the entire dynamic of street racing. Previously, building a fast car required deep pockets or extensive mechanical knowledge. With plate nitrous, any kid with basic tools could bolt on serious horsepower. This democratization created a golden age of street racing in the 1980s, where creativity and tuning skill mattered more than cubic dollars. Insurance companies and law enforcement were not pleased. The sudden proliferation of 300 horsepower Honda Civics and 500 horsepower Mustangs on the street led to crackdowns and increased premiums. Some states tried to ban nitrous systems entirely, but the genie was out of the bottle. Mike's simple invention had given average enthusiasts access to supercar performance, and there was no going back. The professional racing establishment eventually embraced the plate system fully. NHRA and IHRA created specific classes for nitrous cars. The simplicity and reliability of plate systems made them perfect for sportsman racing, where competitors often had limited budgets and a crew support. By the late 1980s, plate nitrous was winning national championships in categories from superstock to top sportsman. Engine builders adapted their designs for nitrous compatibility. Forged pistons became standard for any serious nitrous application. Ring gaps were increased to handle the additional heat. Camshaft profiles were developed specifically for nitrous engines, with less overlap to prevent blowing the nitrous charge out the exhaust. Head gasket technology advanced to handle the increased cylinder pressures. The entire performance aftermarket evolved to support what Mike's $60 plate had started. The evolution continued into the 1990s with the development of the soft plum plate. Instead of rigid spray bars, this design used flexible tubes that could be bent for optimal spray angle. This allowed tuners to fine-tune the spray pattern for different carburetor and manifold combinations. While more complex than Mike's original hard plum design, it maintained the fundamental simplicity of single-point injection. Multi-stage plate systems appeared, stacking 2 or 3 plates with progressive activation. A racer might run a 100-shot plate for launch, activate a second 100-shot plate at the 60-foot mark, and trigger a third plate at half-track. This stepping of power delivery solved traction problems while delivering massive total power. Some pro-modified cars ran 3-stage plate systems worth 900 horsepower on top of 800 horsepower engines. The most extreme evolution was the fogger plate, which used dozens of tiny holes to create an ultrafine nitrous mist. This design, still based on Mike's fundamental concept, could support over 500 horsepower from a single plate. The fogger pattern provided such thorough mixture preparation that engines could survive nitrous percentages that would have been impossible with early designs. Modern electronic fuel injection brought new challenges and opportunities. EFI systems don't have carburetors, so traditional plates wouldn't work, but the principle translated perfectly. EFI plates mount between the throttle body and intake manifold using the same spray-into-airstream concept Mike pioneered. The only difference is that fuel enrichment comes from the ECU rather than supplemental fuel nozzles. The simplicity remains. Today's nitrous plates are CNC machined from billet aluminum, anodized in various colors, and engineered with computational fluid dynamics. But strip away the modern manufacturing and marketing, and you'll find Mike Thermos's fundamental design. The spray angles might be optimized, the materials might be fancier, but it's still just a plate with holes that sprays nitrous and fuel into the airstream. The numbers tell the story. In 1981, before Mike's invention, the total market for nitrous systems was about $10 million annually, dominated by expensive direct port systems sold to professional racers. By 1990, the market had grown to over $100 million, with plate systems representing 70% of sales. Today, the nitrous market exceeds $500 million annually, and plate systems remain the volume leader. Mike Thermos never got rich from his invention. He never founded a company or licensed his design. He kept working at the machine shop until 1987, when he opened a small speed shop in Edison. He still builds custom plates for local racers, charging just enough to cover materials and time. When young racers come in, eager but broke, Mike often helps them out for free, just like he wished someone had helped him. The legacy of the nitrous plate goes beyond just performance. It represents the best of American hot rodding ingenuity, the idea that a teenager with an idea and access to basic tools can outsmart million-dollar corporations. It proved that simple solutions often beat complex ones. It showed that democratizing performance creates a bigger market than keeping it exclusive. Every time someone bolts a plate system to their engine, they're using Mike Thermos's design. Every 150-shot streetcar, every 1,000-horsepower drag racer using staged plates, every grudge racer looking for an edge, they all owe their power to a 17-year-old who thought there had to be a better way. The technical specifications of modern plates would amaze Mike's 1981 self. Current designs flow enough nitrous to support over 1,500 horsepower. Spray bars are now manufactured from stainless steel to prevent erosion. Some plates incorporate burst panels rated at specific pressures. Electronic solenoids provide millisecond precise activation. But the fundamental principle, spray into the airstream and let physics handle distribution, remains unchanged. The nitrous plate system stands as one of the most successful grassroots innovations in automotive history. It took a technology reserved for the elite and made it accessible to everyone. It proved that innovation doesn't require corporate backing or advanced degrees. Sometimes it just takes a kid who refuses to accept that performance should be expensive. Mike Thermos is now in his 60s, still building engines and still advocating for simple, effective solutions. When asked about his legacy, he doesn't talk about the revolution he started or the industry he transformed. He talks about the kids who could finally compete, the barriers that fell, the playing field that leveled. He talks about democratized horsepower and accessible performance. He talks about proving that good ideas beat big budgets. The next time you see a car launch hard at the strip, hear that distinctive nitrous purge, or watch someone gap a car that costs 10 times as much, remember Mike Thermos. Remember that 17-year-old kid who looked at $1,000 systems and said, "I can do that for $60." Remember that sometimes the best engineering comes not from trying to make things complex, but from finding the simplicity hiding within the complexity. That's the legacy of the nitrous plate. Proof that innovation belongs to anyone willing to question the status quo, that the best solutions are often the simplest ones, and that a kid with scrap aluminum and a good idea can change an entire industry. Mike Thermos didn't just invent a nitrous system, he democratized power itself. What's the most innovative speed part you've seen come from a garage inventor? Let me know in the comments below, and don't forget to subscribe for more stories of grassroots innovation that changed racing forever.